Well, it's 10 o'clock. I don't want to keep anyone too long, at least those of you who are here on time. Um, if you saw the post I had earlier, um, there's some new notes on exponential functions, which will probably start today. And the first bit of it is just like exponent rules, stuff you learned in October of grade 10-ish. So that will be interesting. Um, there'll be an assignment shortly today or tomorrow on inverses and the radical stuff. Nothing out to lunch. Similar format to the last one, and I'll probably give you a week or a week and a half to work on it, but a lot of it involves the mapping rule stuff, and it's just kind of the recurring theme is about key points, plotting them, and all of that. And that's what we're going to do with exponential functions. So today, I want to go through quickly these four and their, whoa, sorry, graphs. So y equals 2/3 x minus 2 has a slope. So this is our original function. Pow-ish. That's actually one of the better lines I've done. So this is with radicals. So if I'm looking at y equals the square root of f of x, or this is f of x, um, we can do this. The first thing we need to do is find our two important points where y equals 0 and y equals 1. So I have all of this business down here. Rise to, right here. I'm just for some reason second guessing the graph. And the silence is still something to get used to after having probably one of the loudest classrooms or louder classrooms in the building. It's just talking to myself is still just weird. So we have our point. There's one of them. Our first invariant point is at 0, or well, in this case, -3 and 0. Then I estimate that one somewhere in there. This is linear. We could actually put 1 in here, add 3 times 3 to, like, we could figure that point out. So there's those. The other points we can look for are perfect squares. So the next perfect square after 1 is 4. So coincidentally, we have that is where 4 is. The square root of 4 is 2. That's similar to what we drew yesterday. Oh, I think, because if I do that graph, it's way up here. I think I missed a negative in here. This should be negative. It has to be negative because if not, the graph is. So that's a line. A parabola, if I'm graphing the negative, the vertex, oh, sorry, domain and range. Gosh, is that loud to everybody? The domain is all of the x values less than or equal to -3. The range is y is greater than or equal to 0. Invariant points, -3 and 0. And approximately 9/2. Well, that one's easy to find, -4.5 and 1. And that's what you would be expected to list. So those are there. The vertex for this bad boy is 1 and 9. Over 1, down 1, over 1, down 3. Hey, look at that. So we've got a horrifically drawn parabola, but there is f of x. Y equals the square root of f of x, where, oops. So, invariant points. Well, I want none of this business because that all doesn't make sense. So let's see. We have this point here. We have that point there because the square root of 0 is 0. We want the point that has a y coordinate of 1. Well, that's kind of sucky. So it looks like it's going to go something like that. 1, 2, 3, 4 is somewhere over here. So, oh no. So the square root of that is 2. And the next point, well, 9. The square root of 9 is 3. So we actually get this nice little almost semicircle. Domain of this. Well, x is bigger than -2. X is less than or equal to 1, 2, 3, 4, which you could write as -2 less than x less than 4. The range is y is greater than or equal to 0. Y is less than or equal to 3. We could do the same bit. Invariant points, well, two of them are kind of easy. -2, 0, 4, and 0. The other ones are a little bit tricky. Approximately -1 I don't know, 8 and 1. And for symmetry's sake, let's say approximately 3.8 and 1. Could we solve that? Sure. If you want to, that's great, but there's really not a whole lot to worry about. So these can look slightly different if it's a parabola. Oh, this one has a vertex of -1 and -4. -1, -4, over 1, up 1, over 1, up 3, up 5, and that's probably all we need to do. There's something like that. Hopefully you guys are all artistic enough to draw that there. Well, let's pick green because it's fun. Y equals the square root of f of x. So again, the invariant points, one of them is -3 and 0, 1 and 0. Those are easy. So we start here. Well, 1 is going to be somewhere up. No. Why do I keep doing that? 1 is somewhere over here. 1, 2, 3, 4 is about there. So 2 is here. So we get this little curvy thing going that way. Same idea, because I'm horrific at drawing. 1 would be about there. 2, 3, 4. So 2 would be about here. And we get this. Those are supposed to be symmetric. I apologize for my horrible drawing. This is one on the left side that the domain is x is less than -3. On the right side, x is greater than 1. You can't combine those. The range is the same. Y is greater than 0. -3, 0, 1, 0. And then we can say -3.2-ish and 1. 1.2-ish, and 1. That's supposed to be that tilde, but it's just poor writing. Yeah, go away. Sorry. X squared plus 2. Oh, that's a little different. 0 and 2 over 1, up 1, over 1 more, up 3, up 1, 2, 3, 4, 5. So that's going to be kind of now if we take the square root of any of these points, is anything going to be invariant? Well, let's do it in orange for fun. There's actually, because this doesn't cross the x-axis, it has no x-intercepts, it actually has no invariant points. Because the square root of 2 is about 1.4. The square root of 3 is about 1.7. The square root of, what's this? 1, 2, 3, 4, 5, 6 is 2 point something. 2.5-ish. I can pull up my 6. Square root of 2.4. So 2.4. We can go up. The square root of 10 is 3 point a little, because that point would be at 10, because up 5, you'd have our actual graph would be up here. So we get this. It's not a parabola per se. It's just a flat little, like a stretched out, spread out curve. Domain. X is part of the real numbers. X can be anything because there's no, it's never below the x-axis. Range, y is greater than or equal to, because the minimum is 2, and that is none. So this whole thing that's important in this little section is the idea of invariant points, points that don't change when you graph them. And that's what I should have gone through here. Strategies to sketch the square roots. Plot the invariant points, the points that don't move. Join them with a smooth curve above the function. Yeah, my graph is poorly drawn, but it just depends on the pitch of the line. Plot other key points, perfect square y values you can get a square root of. To make then you make a continuous curve. Restrictions on the domain. The minimum is at an x-intercept, undefined, where f of x is. That's a mistake. That should be less than. That's what happens when you type notes at 10 after 6 while kids are still asleep. You're still asleep. So that is that part. For the radical stuff, most of the assignment will be on the first 2 parts, just because that's the stuff that's we do a little bit more. I might add 1 question, maybe plot the graph of a square root of a line, something like that. Okay, we're good. Any questions? I don't even know who's here. Hi, everybody who has showed up after I started and said hello. Hopefully getting up at 10 o'clock is not that difficult for you anymore. At least you guys it isn't. So that's that. I will update that later. The next kind of, it's a big group of things, is the stuff on exponential functions and log functions and laws of logs and all sorts of things which come up a lot in calculus. You'll see exponential or logarithms in chemistry 12 if you take it. I did suggest This is a slideshow. I want to look at a couple of slides. This is, you can take a look, it's about exponential functions. Hopefully it doesn't have sound. Oh, here we go. We'll talk about those laws of exponents here in a second. This is taking way longer than it did. Exponents in computer games. Not really worried about that. Viral marketing. If one person tells 10 people and 10 people tell another 10 people, it grows and grows. Compound interest, which you did in GMF in grade 10, is an exponential growth. That's why they tell you to start investing long ago. Population increase, whatever, fuel, that's in debt if you don't pay your debt. Bacteria and viral growth. And there's been all sorts of different things about these in the news. I think theirs is pretty. I don't understand it. Well, I do know how my internet is slow down here because I'm streaming all sorts of stuff to all of you wonderful people. But no, I wasn't looking for the helicopter issue. Here we go. There's all sorts of these out there now. These COVID-19 graphs and whatnot. Hopefully this has some of the world stuff. What pictures? Okay, maybe CBC's was better. So when you look at these graphs, this is Quebec's because Quebec is, there's raw, this is total cases, deaths and recovered, but that's a 7-day average. If I go to cumulative, this is growing slow, 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 low, slow, and it comes up. New Brunswick, we got as lucky as they come. But those graphs are not the ones that I was thinking they were. I get confused between CPC and CTV. Oh. Where are your graphs? Oh, there we go. These things are everywhere now. Oh, they give you numbers. There's 3.5 million in the world, 60,000 in Canada. We're doing quite well. View as chart. Select a region to display. So I don't know why it's a web page is slowing down your browser. I think it's this web page. Canada. What? Oh, here we go. We got something. Oh, daily deaths. Well, I'm not as concerned about those. Because daily new cases, no. Buzz off. New cases, it's good when those go down. But, no, not cumulative deaths. I don't care about that. Cumulative cases. This is still a fairly linear scale. When you get to some of the worldwide ones, which I'll have to find, there's Johns Hopkins in the States has, I'm not going to sit and I'll find some and go through them. You have to watch the scales of the graphs because a lot of the big ones now have they're on a logarithmic scale which goes 10, 100, 1,000, 10,000. So it looks kind of nice. Let's see if this can, maps. World maps. So if these things are on a linear scale, the growth is ridiculously quick. If it's on a logarithmic scale, which we'll talk about when we look at those, the logarithmic scales are the ones that kind of look like they're coming up and flattening out because there's not a whole lot of increase. That's looks like a linear scale because it's growing. A logarithmic scale, this one should, if I click it, that's where we're seeing the flattening because 1,000, can I make that bigger? Wow. Oh, there we go. So 1,000, 10,000. So there's 9,000 cases different here. 10,000, there's 90,000. There's 900,000 different there. So it looks, this is flattening. We're not getting a whole lot of stuff. This is exponential growth. And if it went unchecked and we didn't do social distancing and you weren't sitting at home in your living room and you were sitting in my room and we were having a wonderful, lively discussion about Lord knows what, this slope would have gotten higher and higher and higher. And we would have had all sorts of issues. So that's exponential growth. Where am I going? So the functions that we're going to be looking at are in the form of y equals b to the power of x. And so I'm not sure why they use b. B has to be bigger than 0. B can't be 1. If b is 1, it's really boring. The key is the variable is in the exponent, hence exponential function. The base changes. The base can be, we'll look at 2s, 10s. Those are the two common ones. Then there's the natural logarithm, which is the base, the letter e, which we'll also mention quickly. I want to review some exponent rules because they're going to come in handy. This is all stuff that you did in grade 10. I know that because I taught NERF last semester, so we spent all these days on this. The product rule, a to the third times a squared is a to the 3 plus 2 is a to the fifth. We can look at it. A cubed is a times a times a. A squared is a times a. Well, 3 of them times, so how many a's do we have? A to the fifth. Instead of writing all of that out, we know that we can just add those exponents. The quotient rule, in this case, I need an equal sign, is 7 minus 3. So this would be a to the fourth. A to the seventh in the numerator. Why didn't I do a smaller one? That's 5, 6, 7. A cubed. Now, this is where language kind of causes a little bit of trouble. We normally say if I have a over a, those cancel. And fundamentally they do, but it's not an actual cancellation. A divided by a is 1. This a divided by that a is 1. It's not that the variable disappears, it's just something divided by itself is 1, so those all go away, and we're left with a to the fourth power. The power law, if it's a power of a power, well, not 2 times 2, but 2 times 3, a to the sixth, because we have a squared, which is a times a. Well, if it's to the third, we're repeating that multiplication 3 times, and now we end up with a to the sixth, because 1, 2, 3, 4, 5, 6. product of a power and or power of a product and power of a quotient are kind of combining these things. If we have product of a power, we're going to take that 2 and just basically do it as if, well, I have 3 squared. I have a to the, oh my gosh, a to the 5th squared, b to the 4th squared. Because it's all multiplication, so you can manipulate it kind of how you want. Well, 3 squared is 9. A to the 5th squared is a to the 10th. B to the 4th squared is b to the 8th. We're applying that exponent to each one. The quotient is the same. This you can look at as a to the 6th squared divided by 5 squared. And if you're good with exponents and had no issues or anything like that, you can go, well, I know this is a to the 12th, and this is not 5, but 25. So we can expand those out. Zero exponent is my favorite one. 2 to the 0 is 1. These two are here because they're tricky. And then this one here is, I got a whole bunch of stuff, and I just picked all sorts of random numbers. So that one is 1. These two are very different. This one is equivalent to -1 times 2 to the 0. This one is -1 times 2 to the 0. Because that bracket is there, well, 2 to the 0 is 1. So this is -1 times 1 is -1. This is -1 to the 0 times 2 to the 0. Well, that to the 0 is 1 times 1. Brackets are important. Some calculators are smart enough to know what you mean. 2 negative x to the y gives me an exponent. -2 to the 0. This one assumes that you mean a bracket, but I've got other calculi, which that fundamentally bothers me now that I think about it. Most calculators typing that is different. Why is something to the power of 0, 1? Well, a to the 4th over a to the 4th is something divided by itself, which is 1. Okay, that's cool. But with exponents, a to the 4th over a to the 4th is 4a's over 4a's. Well, we said a over a. Those cancel to give you 1. Those cancel to give you 1. Those cancel to give you 1. No matter how many of these you have, those cancel to give you 1. Well, 1 times 1 times 1 times 1 is 1. Or, well, so a to the 4th minus a to the 4th is a to the 0. Equals 1 times 1 times 1 times 1, which is 1. So that's why those are. I'm going to do these two and call it quits because it's 10:30. Rational exponents, again, grade 10 and some pre-calc 11. The kind of a to the x over y is the y-th root of a to the power of x, or the y-th root like that. So you can do it in different directions. So if it's a half, this is just the square root of 4, which is 2. And on one of my graphing calculators, the square root is a second function button. It's actually easier for me to use. Like if I'm doing for this one, it's half is 0.5. Well, there's the square root of 4. This one is the square root of 9, which is 3. Ooh, a little bit trickier. The cube root of 125, which is 5. But it's just about rewriting and recognizing cube root of 8 squared, or the cube root of 8 squared, because they both are the same. 8 squared is 64. The cube root of 64 is 4. If I do the cube root first, the cube root of 8 is 2. Squared. Whoa, sorry. The cube root of 64 is 4, and that is 4. So it doesn't really matter which direction you do. Some numbers are easier. If you don't have a perfect root, well, do the exponent first. But that's stuff you did in grade 10 and pre-calc 11, so whatever. Negative exponents. And that's it for today. So writing this out, well, we could say a to the 3 minus 5, which is a to the negative 2. Okay, that's cool. A, 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 A. Those go away, those go away, those go away. So we're left with 1 times 1 times 1 in a numerator, which is 1 over a squared. So a to the minus x is 1 over a to the x. And we use this, we're going to use this idea when we do some exponential functions. So a to the negative 2 is 1 over a squared. I can't remember why I have those. 1 over 2, 2 to the negative 2 is 1 over 2 squared, which is 1 over 4. I hope I'm not going too fast. Nobody's yelled at me too much yet. Normally somebody does. I might have dropped a couple people because they're like, this is foolish. Or they had to go to work. So we could have 3 over b to the negative 5. Well, I've got a negative in the denominator. So this is 3 over 1 over b to the 5th. Well, 1 over b to the 5th dividing by a fraction we don't like. So the reciprocal of that is b to the 5 over 1, which is 3b to the 5th. Tomorrow we'll look at some factor trees and whatnot if you've looked at those. But once we get through those, just looking at evaluating or converting things to exponents, that's like 5 minutes. The graph of y equals 2 to the x. We'll build a table of values, do the sort of things that we do with other things. We'll look at a half to the x. We can look at changing bases and then transformations. So that's it for today. I mean, that's all. I don't know why it does that. Oh, that would have been, if I click that, it gets rid of all my ink. So that's all for today. If there's no other questions, you are free to go. Enjoy your day. Check later for the next assignment, but I'll post that an assignment is posted once I get it settled, if that's today or tomorrow morning. If not, have a good one. Don't catch COVID-19.
Thank you, Kenny.
Welcome.